Hi everyone, I'd like to thank the members of Service Science Best Paper Combination Committee for inviting this talk. My name is Shixin Wang, and I'm an assistant professor at the Chinese University of Hong Kong. I'm happy to share my recent work on the power of simple menus in robust selling mechanism. When a seller designs a selling mechanism, he needs to consider customers' willingness to pay. For example, if the price is $5.99, only customers with a willingness to pay higher than this value will buy the product. And the seller wants to maximize the expected revenue, which is the price multiplied by the purchase probability. If the seller knows the willingness to pay is a 3-point distribution, then he chooses the price that maximizes his expected revenue. However, in practice, the customer's willingness to pay can take arbitrary value in a wide range, so it's challenging to obtain the exact willingness to pay distribution information. And thus, the seller may take different approaches to estimate the willingness to pay distribution. He could conduct market research to estimate the range or the mean of willingness to pay and adopt price experimentation to estimate the quantile of willingness to pay. When we are using price experimentation, sometimes we do not have enough transaction data, or we cannot adjust the price too frequently. So we have to wait for a long time to get an accurate estimation of the conversion rate for these prices. So it's more practical that the seller only has some sparse quantile information. For example, we might know the proportion of consumers who are willing to buy the product at a price of 200 is 80%, and proportion of customers who are willing to buy the product at 800 is 40%. Then a naive pricing strategy might be to estimate willingness to pay distribution based on this prior information. However, if the true distribution is a different distribution, then the optimal pricing in the first distribution may result in a significant revenue loss in the true willingness to pay distribution. So this motivates the study of robust screening that the seller hopes to have a good revenue under different valuation distributions consistent with the prior collected information. The robust screening may have many different types of implementation. For example, randomized pricing is a simple implementation of robust screening. So suppose an online shopping platform posts a price at 1,000 with half probability and run a promotion of 500 with half probability. Then this randomized pricing strategy achieves a revenue of 300 in both distributions in our example. So now we know the robust screening has better performance compared to posted price. In our example, where there are only 4 different valuations, the optimal robust mechanism could be a randomized pricing between 2 price levels. However, in practice, where there could be many different valuations, the optimal mechanism solved by the robust screening is difficult to implement because the price density function is continuous in price, and there are infinite number of price levels that have positive price density. So this means the seller should change the price frequently, which makes the pricing system hard to manage, or it may confuse the customers. So the current study focused on the robust posted pricing and robust screening. The advantage of robust posted price is its simple implementation. However, the performance of robust posted price is often low compared with the robust screening. And robust screening has high performance, but is difficult to implement. So in view of the gap between the theoretical performance and practical application of robust screening, our research question is, can we develop simple selling mechanisms that offer a limited number of options, yet maintain a strong performance guarantee? And how effective are the simple selling mechanism compared with the optimal robust screening without menu size constraint? Okay, so the seller considers an N-level pricing scheme and needs to determine the price levels and pricing probabilities. Since we don't know the willingness to pay distribution, we adopt a worst-case distribution within an ambiguity set that minimizes the ratio between the revenue achieved by the seller's mechanism and the best possible revenue that the seller could have obtained had he known the willingness to pay distribution. And then we use this performance ratio as the performance measure. The feasible price distribution includes all endpoint price distributions within the feasible valuation range. When we consider robust deterministic pricing where n is equal to 1, then the pricing probability is fixed. The decision is only the pricing support. When we consider robust grading where n is equal to infinity, the support is already fixed and the decision is only the pricing probability. However, for our n-level pricing scheme where n is finite, it is more challenging since both the price support and probability are decision variables. And these two sets of decision variables do not interact each other linearly in the objective. So the problem becomes non-convex. So the technique and approaches adopted in the robust pricing and robust grading may not apply for the finite n-level pricing scheme. So our contribution is to provide a unified approach to analyze the n-level pricing problem, and then provide a closed-form optimal solution for some simple ambiguity sets. So for example, we solved the optimal n-level pricing scheme for the support ambiguity set, and we solved the closed-form optimal solution for two-level pricing for the mean upper bound ambiguity set. And also for the quantum ambiguity set, we solved the optimal solution for the one-level, two-level, and infinite-level pricing scheme. For example, in the support ambiguity set, we compared the competitive ratio under different menu sizes and competitive ratio achieved by the optimal robust grading scheme with infinite price levels. So here we plot the ratio by one-level pricing in black, two-level pricing in blue, and five-level pricing in green. So it shows that for any given support information, there is a significant improvement from one-level pricing to two-level pricing. And even if we only have 5 price levels, the competitive ratio is close to that of the robust grading scheme. And we also have similar observations for the mean ambiguity set, quantile ambiguity set, and mean variance ambiguity set. So there is a significant improvement from one-level to two-level pricing. And for many information, the performance of two-level pricing is close to that of robust grading scheme. So in summary, we introduced the n-level pricing problem and propose a unified framework that addresses a broad class of ambiguity set, and we derived closed form under some simple ambiguity sets. So from our observation in different ambiguity sets, randomizing between two prices can significantly improve the performance from the deterministic pricing. And this mechanism is simple to implement in practice. Thank you so much for your attention. I'm looking forward to seeing you at Seattle.